morning. We shall begin with the topic from semester 2nd, that is study of block elements. Some part of this topic that we have already studied at our BSc Part 3 level. Some detailed studies expected at this level. So in this topic, we are going to study the two series of the periodic table, that is 4F series known as lanthanide series and 5F series, that is actinide series. Both these series comprises of in all 15 elements. So we are going to study in all 30 elements from lanthanides and actinides. I am going to show you the schematic representation of the periodic table, wherein you can see how the F block of the periodic table that forms a separate block comprising of in all 13 elements. Now, in 4F block elements known as the lanthanide elements, we are going to study first of all the electronic configuration. Then we are going to study the oxidation states, then the magnetic properties, then the colored ions and the applications, including the lanthanide contraction. While studying the actinide series, we are again going to see the electronic configuration, the oxidation states, and the magnetic properties, and the all other relevant properties associated with the 5F block of the periodic table. Now, I would like to show you one graphical representation, schematic representation of the periodic table, where we can find that there is a separate block known as a F block of the periodic table. Here, if you see, now here, this is a schematic representation of the periodic table, where on extreme left hand side here, this is the first A group of the periodic table known as alkali metals. This is second A group of the periodic table known as alkaline earth metals. And here third B group starts. So the first A group and second A group elements are commonly known as a S block of the periodic table. While on extreme right hand side here, a separate block is there that is known as a P block of the periodic table, which comprises of the zero group elements, what we call as a inert gas elements from helium to radium. Then in between S and P block of the periodic table, this is a D block of the periodic table, which comprises of 3D series, 4D series, 5D series, and 6D series. So as these elements are present in between S and P block of the periodic table, hence are commonly known as the D block of the periodic table. Another word that is also given for these elements is a transition elements. The word transition means those elements which are situated or placed in between S and P block of the periodic table are known as a transition. So they make a transition between the following and the preceding, that is the S and P block of the periodic table. And here these are known as this is first period, second period, third, fourth, fifth, sixth, and seventh period. So sixth period, which starts with cesium atom number 55, then there is a barium, and after barium from group third B of the periodic table, here a lanthanum element is there that is known as a atomic number 57, and there comes a series of almost 14 elements, including the lanthanum, that forms the 15 elements from atom number 57 to 71, where the incoming electron preferentially enters into 4F orbital. Then the seventh period, at this point, again, there comes a series of almost 15 elements here from actinium to lawrencium atom number 103, 89 to 103. So all these elements commonly known as the F block of the periodic table, where the first series, the major orbital or electron subshell is a 4F, and for this actinide series, the 5f orbital is there. So here they have shown that there are 14 elements are there, but if we include the first element, that is actinium, and first element lanthanum, then the total is 15. So all these elements are grouped under the F block of the periodic table because the incoming electron or new electron preferentially enters into 4f orbital or 5f orbitals respectively. Or there here, all these elements are characterized by presence of incompletely filled 4f orbitals or incompletely filled 5f orbitals, and hence are known as a F block of the periodic table. Now, there are 15 members. Which are those members? Just see here. I would like to show you all the 15 members in simple diagrammatic form. That is having almost 15 members. So what are the characteristic features of all these elements? Here, the elements in which last electron enters into F subshell, that is either 4F or 5F of the anti-penultimate shell. Anti-penultimate shell means 4F, 5D, 6S or 5F, 6D and 7S. The 4F or 5F orbital is known as a anti-penultimate shell. These are also known as a inner transition element. I would like to tell you what are these inner transition. Here, I have just now told you that the D block elements are also known as a transition elements, and the elements, that is the lanthanides or the actinides, these 15 members are included here from third B group. So transition elements in which the third B group also comprises of the elements of 15 elements, total of 30 elements, and hence these are known as the inner or sub-transition elements. So this is the meaning of inner or sub-transition elements. So these are also called as the inner transition elements. They are also all heavy metals. They also form complex salts. That means they involve in complex formation. They also show variable oxidation state that I will emphasize in the due course of time. Their compounds are generally colored and actinide elements are radioactive. So these are some common characteristic features of all these elements. Now, today we shall begin with the series that is named as the lanthanide series, wherein we are going to see how the different electronic subshells are filled by preferential occupancy of 4f orbital. Just take a look at this. If you want, you can also take a note. I'm going to distribute the notes also in due course of time, but wherever you require, you can also add the important notes. So the 4f elements are known as a lanthanide elements or lanthanides. The elements are named as the lanthanides because lanthanum being the first member of the series having atom number 57, and because of this name, the series is named as a lanthanide series. So I am going to prepare one tabular form that will enable you for the better understanding of the electronic configuration. So I shall write here the electronic configuration. For this electronic configuration, first I shall write the atomic number, then I shall write the symbol of the element, then I shall write the name of these elements so that we will become familiar with the names, and last column is a observed electronic configuration. Now, first of all, I shall write the atomic number and the symbol with the respective names, and then I shall finish with the electronic configuration. So you have to listen and see this electronic configuration very carefully and attentively. First is atom number 57. Symbol is La. Name of the element is lanthanum. Then atom number 58. Symbol is Ce. Name of the element is cerium. It is not curium, it is a cerium. Atom number 59. It is a Pr. Name of the element is a praseodymium. You should remember the correct names of all these elements. Atom number 60. Hindi, known as neodymium. Then 61. It is a PM. Name is a promethium. Then 62. It is a SM. Name of the element is samarium. Then 63. It is a EU. Name of the element is europium. EUROPIUM. This is a europium. Then 64 is a GD. Name is a gadolinium. You should by heart this series. That will definitely enable you for the better understanding, because everything that is depend upon all these three parameters: atom number, symbol, and the name of the element. 65 is a TB. Name is a terbium. Then 66 is a DY. Dysprosium. Then 67 is HO. Name is holmium. Then 68 is ER. Name of the element is erbium. Holmium, erbium. Then 69 TM. Name of the element is thulium. Then 70 is a YB. Name of the element is YTTERBIUM, ytterbium. And 71 is LU. Name is lutetium, LUTETIUM. So these are all 15 members starting from lanthanum to lutetium. So they comprise the presence of partially filled or partly filled or incompletely filled 4f orbital, and hence are known as a lanthanide elements, or commonly known as a 4f elements. Now, before going to start with the actual electronic configuration, I would like to tell you some background of this electronic configuration that will be very easy for the clear understanding of the electronic configuration. Now, in the beginning, I have told you that first A group of the periodic table, where the sixth period, which starts with cesium, atom number 55, then comes barium, atom number 56, and then under third B group of the periodic table, here a series of 15 elements, that is a lanthanum to lutetium, that is atom number 71, which comprises of 15 elements. So this we have seen that the sixth period, which begins with cesium, atom number 55. So first of all, we have to arrive at the electronic configuration of cesium, for which first of all we shall see the electronic configuration of xenon, having atom number 55. Xenon is having the outermost electronic configuration as a 5s2 5p6. So total number of electrons are 54. Now suppose if we want to write the electronic configuration of cesium, then in terms of xenon core, we can write xenon means we have written almost 54 electrons, and after this the next energy level available after 5p is a 6s, so we can write 6s1. So we have written the electronic configuration of cesium comprising of 55 electrons. So xenon is 54, and then cesium 55, just we have added one more electron. So after cesium, barium is there. So for barium, atom number 56, we can write the electronic configuration in terms of xenon core. Simply we have to add one more electron in 6s orbital. So 54 plus 2 is 56. Now after barium, the next orbitals are 5d and 4f, which are almost empty. So the maximum occupancy of 6s orbital is of 2 electrons. Now the 57th electron after barium, the 57th electron may enter into 5d or 4f. Now for this purpose, I would like to show you one energy diagram of all these three orbitals. Say for example, this is the increasing energy of different orbitals, and this is the atomic numbers of the elements 57, 57, 58, 59, 57, 58, 59, and 60. That is the lanthanum, cerium, praseodymium, neodymium, and these are the different energy levels. Here it is seen that this energy level having low energy, this is known as a 6s. This energy level next to 6s is a 6d, which is little bit higher than 6s, and next highest energy level is a 4f. So this is a situation which is before atomic number 58. So before atomic number 58, 6s is having low energy, but after atomic number 58, see this energy level which is having high energy. Now before 58, 5d orbital, and after atom number 58, 5d orbital is having almost same energy. But if we look at the energy of 4f orbital after atom number 58, it is having low energy. This is a 4f orbital, and it is having high energy before atomic number 58. So as per above principle, low energy orbital filled first and successively higher energy orbitals are filled. Now here at cesium, I think all the three energy levels are almost having same energy. So one cannot decide where the electron is actually entering into 5d or 4f orbital, because 6s orbital is filled at barium. So 2 electrons are already filled. Now the next choice for incoming electron for lanthanum will be 5d1 and 4f0. So according to above principle, low energy orbital filled first, but here at barium this orbital is filled, and at lanthanum now the incoming electron enters into 5d orbital. So for this purpose, I shall write the electronic configuration for lanthanum 4f, 5d, 6s. 6s orbital is filled at barium. So 54 plus 2 is 56 plus 1 is 57 and 4f0. So this configuration is strictly according to this energy level diagram. Now, if we move one step further at cesium, what will happen? Here at cesium, almost all the three energy levels having equal energy content. So for this purpose, I can write the electronic configuration as 6s2, then 5d0 and 4f2, because here all the two incoming electrons now enter into 4f2 orbital. In some books, you may find that 5d1 and 4f2, but I have written purposefully here that observed electronic configuration. So this is a observed electronic configuration. Now, if we move one step further, that is a lanthanum, cerium, and praseodymium. What will happen at praseodymium? At praseodymium, 4f orbital is having almost low energy than 5d, and 6s orbital already filled at barium. So no question about 6s. We have to think about only 5d and 4f. So while writing the electronic configuration for praseodymium atom number 59, we have to write all the electrons, those should be coming in 4f orbital. That means after cerium, the 4f orbital becomes decisively more stable, and hence we can write the electronic configuration as like this. No question about 6s. We have tried 2 electrons directly. 5d 0 because 5d orbital is having high energy as compared to 4f. So 5d 0 and all the 3 electrons. So 54 plus 2 is 56 plus 3 is 59. So all those electrons now enter into 4f orbital. So some authors, they have shown that it is rather difficult to show whether the electron, incoming electron, actually enters into 4f orbital or 5d orbital. So because there is very small energy gap between these two orbitals. See here, this is a small energy difference, but the cumulative difference is large enough from the average energy, but the difference between the successive energy levels is very small. And when we pass towards other elements, means as the atomic number increases, this energy gap also increases between 4f and 5d. So for this purpose, for neodymium, we can write xenon 4f 5d 6s. So for neodymium, there is no question, as we know that we can write directly 6s2 5d0 and 4f4. So 56 plus 4 is 60. Then on similar grounds, we can write 4f 5d 6s 6s2 5d0 and 4f5. So 56 plus 5 is 61. Then come to samarium, xenon 4f 5d 6s 6s2 5d0 4f6. So 56 plus 6 is 62, samarium. Now come to europium, xenon 4f 5d 6s. So 6s2 5d0 and 56 plus 7 is 63. Now come to gadolinium, atom number 64, which is a central element from this series, xenon 4f 5d 6s. So 6s2, and here according to this sequence, the occupancy of electron should be like this: 4f8 5d0, but there is a little interruption. That means instead of 4f8, it becomes 7, and one of the electron is exchanged with 5d. So the observed electron configuration is 4f7 5d1 and 6s2 instead of 4f8 5d0 6s2. So observed electron configuration is 4f7 5d1 and 6s2. So this is a 5d1. Now come to terbium, atom number 65, xenon 4f 5d 6s 6s2 5d0 again and 4f9. So 56 plus 9 is 65. Now come to dysprosium, 66, xenon 4f 5d 6s. So 6s2 again 6s2 5d0 and 4f10. So 56 plus 10 is 66. Then come to holmium. Holmium, now xenon 4f 5d 6s 6s2 5d0 4f11. So 56 plus 11 is 67. Come to erbium, xenon 4f 5d 6s 6s2 5d0 4f12. So 56 plus 12 is 68. then 69 xenon 4f 5d 7s sorry 6s to 5d 0 4f 13. So 56 plus 13 is 69. Come to getter BM xenon 4f 5d 6s to 5d 0 4f 14. So 56 plus 14 is 70. And lutetium xenon 4f 5d 6s to 4f 14, which is filled at Ytterbium. Now here I would like to show you once again this energy level. So here 4f 14, then 6s is already filled at barium. Now the choice for incoming electron will be only for 5d. So the 71st electron now enters into 5d orbital. Hence it becomes like this: 4f14, 5d1, 6s2. So this is how we have arrived at the electronic configuration for all these elements. Now, what are the drastic features of this electronic configuration? Now, I would like to emphasize the drastic features which we have seen here, that at atom number 63, here the electronic configuration for europium is xenon 4f7 5d0 and 6s2, and at ytterbium atom number 70, the electronic configuration is 4f14 5d0 and 6s2. Now here, if we look at these two anomalies of electronic configuration, then it is seen that at europium atom number 63 and at ytterbium atom number 70, the 4f orbitals are half filled or 4f orbitals are completely filled. So as we know one rule which states that completely half filled or completely filled orbitals, they offer extra stability, so as to offer extra stability to the corresponding atom or ion. The electron configuration is as like this. So those configurations which are either half filled or completely filled, they offer extra stability on account of the half filled or completely filled electronic subshell. So this is how we can study the electronic configuration. So you should remember, while understanding the electronic configuration for all these elements, that because the 4f orbital, which becomes decisively more stable after cerium, and hence this orbital becomes decisively stable and it is having low energy. So incoming electron would enter into 4f orbital rather than 5d orbital. But the case is exactly reverse as in case of the lanthanum, which is before atomic number 58. The case is exactly reverse. Before cerium, the 6s orbital is having low energy, but after cerium it is having high energy. Before atom number 58, 4f orbital is having high energy, but after atom number 58 it is having low energy. So this is how we can see that there are different authors, they have put forward different electronic configuration, but the electronic configuration, however, that we study here, that has been universally accepted, and hence whatever other parameters that we are going to study in due course of time, those are wholly depends upon all these observed electronic configuration only. So you should not make confusion amongst yourself, that you have to consider only the observed electronic configuration. If you try to write the electronic configuration, that is ideal electronic configuration, then there will be a lot of confusion may be taking place. And hence, in order to have the clear understanding of all these of the electronic configuration, you should know the observed electronic confusion only. So while allocation of electrons, it is not always possible to allocate the electrons only in 4f orbital, because initially the 5d orbital having low energy than 4f, and hence incoming electron that has entered into 5d orbital. Now, different scientists were thought of in the early days that why should we include lanthanum in 4f series, because it is having 4f orbital which is completely empty. So there were lot of discussion where took place in the early days, and later on it was found that lanthanum also shows the similar chemical and physical properties as those were exhibited by all those 14 elements, and hence later on lanthanum was included in the series, and hence we consider 15 elements rather than 14 elements. So this is how there were lot of interruptions while writing the electronic configuration. So as I have already told you that the completely half filled and completely filled configurations, they offer extra stability. So the Zoom meeting, it shows only 1 minute has left. You have to just click again the same link and you have to rejoin, and we shall begin with the next aspect of this topic, that is known as the oscillation state. So thank you. You have to join once again by clicking the same link.